When building a robot, one of the things that you have to decide is what computing resource you're going to use in order to run your software. This is the device that's going to interact with your sensors and actuators to actually have the robot do something interesting or useful. However, there's so many options available, and if you just look up random kits, you'll see that some of the kits look identical, but one uses an Arduino or a Raspberry Pi or a Jetson Nano. You can even just use a desktop computer sometimes. So how do you know which device you should be using and the trade-offs between choosing one over another? In today's video, we'll go through a few options and we'll talk about the things you should be thinking about when deciding which one is the right one for your robot. Here's a list of all the companies that I could think of related to computing resources for a robot. And I'm sure if you Google a little bit, you'll find a ton more. So what is the difference between them? Well, one difference is that some of these companies manufacture the actual chips that are part of the computing resources, like the CPUs or other elements on a board, while some of them manufacture the entire board, bringing those elements together to provide you an easy-to-use experience. In general, I categorize computing resources into three categories: microcontroller, single board computer, and then desktop PC. The first category is the microcontroller. Arduino is probably the most popular and well-known brand or company within the microcontroller space. Now what they do is they just manufacture boards. They don't manufacture the actual microcontroller or CPU chips. They get these chips from other companies like Microchip Technology or ST, and they put them on a board and bring all of the elements you need together in a single place. The difference is that they have a very comprehensive ecosystem that makes programming the microcontroller much easier. They have lots of tutorials, lots of open source libraries, and a big community around using the Arduino ecosystem of microcontroller programming. Now you could purchase these chips directly from the manufacturer like Microchip or ST or NXP or whoever. And a lot of these companies have development kits or evaluation kits or whatever that put their chips on a board for you, similar to like what you get when you purchase an Arduino. The difference is that you don't get the Arduino ecosystem. So you would have to use whatever tools the manufacturer themselves uses to program that chip. Arduino takes some of that complexity away from you, but then locks you into their ecosystem. So what are the advantages of a microcontroller? They're small, low power, and low cost. If you're using Arduino, they're very easy to set up. If you're not, then your mileage may vary, because it really depends on the level of support that the manufacturer is willing to provide. They don't have an operating system, so they usually boot very quickly, and they're easy to use to interface with simple devices like LEDs, buttons, or some other hardware that is kind of specially designed for interfacing with a microcontroller. Because they have no operating system, then the commands you write have a very deterministic workflow. You can tell how long your application is going to take to run, and you can kind of get more precise timing than some of the other options. And writing your application for a microcontroller can be fairly simple. It's one big loop, and your program just keeps executing in that loop forever and ever. So then, what are the disadvantages? Well, the first one is that you may not be able to interface with some more complex devices. Like if you want to communicate with a USB webcam, you generally can't do that directly into a microcontroller. Because they have no operating system, also some of the things you might expect to be able to do, you can't do. So interfacing with displays like a monitor, or interfacing or trying to save elements to disk can't easily be done. And lots of times you need additional hardware to do that, and you're the one writing the code to coordinate that those operations. In a desktop PC or a single board computer, the operating system is handling that work for you. Another disadvantage is that you're going to have to program in the language provided by the manufacturer of the board or the chip. That's typically going to be C or C-like language, maybe C++-like. But if your favorite language is Python or JavaScript or something like that, you're probably not going to be able to program in that language. Finally, the way you write a microcontroller program can be a little bit tricky for a beginner. If you're used to programming but have never programmed a microcontroller before, then the idea that you basically have one big loop that never ends can be a little bit difficult to get used to. It's not like a typical program where it runs and then it terminates at the end. It just runs forever, and when it gets to the end, it just starts over again. The next category of computing resources are single board computers. Now, I would subcategorize this into two variants. A basic variant, such as a Raspberry Pi or a BeagleBoard Black or something like that, and the system on a chip variant, like an NVIDIA Jetson or an AMD Xilinx Kria. So what is the difference between these two? Both the basic variant and the system on a chip provide all of the elements you need to have a computer all together in a small package and a single circuit, hence the name. So this would easily be able to provide your display, write to disk, manage memory, all these other things, all together with your processing unit. But the system on a chip variants typically are more powerful because they put some of these elements, at least, into the chip. So they can communicate between these elements faster and they can be more powerful. Also, they tend to add kind of a little bit extra. So they maybe add some FPGA element or some more advanced GPU element or some other processing unit that's highly specialized. So the advantages of a single board computer, especially over a microcontroller, is that it's going to be more powerful. These are fairly comparable to like an older laptop, maybe 2 to 5 years old, in terms of the processing power that you'll get out of a single board computer today versus a microcontroller. Microcontrollers are much less powerful in comparison. They do have an operating system, which typically is Linux, that you can then use to help you coordinate a lot of the operation. So if you want to write to disk, there's already an operating system there to do that, and you don't have to worry about writing your own. It also means that you should be able to easily communicate with displays, use networking, those types of things that you typically expect as normal from a computer. They generally have more memory than a microcontroller as well, and they can use removable memory. So a lot of single board computers use a micro SD slot so that you can add whatever size memory you want to your single board computer. Also, because they're using a operating system, you have access to a lot more libraries and tools than you would have with a microcontroller. So if you're trying to use like an OpenCV or a machine learning algorithm or framework, generally speaking, it'll be easier to get that on a single board computer, which would be very difficult to do with a microcontroller. And because of that, you can interface with more complex devices like USB webcams or basically any kind of USB device via a single board computer, which is much more difficult than a microcontroller. Finally, you have a wider range of programming language options. So because it is an operating system, you can do most of the things that you can get with any desktop computer. So then what are the disadvantages of the single board computers? Well, the first is that they're going to be larger in general. They're going to use more power, and they may be more difficult to set up than a microcontroller. You're relying on the manufacturer of the board to help you create the underlying hardware drivers. So if they're using Linux as their operating system, they're generally the ones who are ensuring that the hardware that they've created is correctly supported by that operating system. If you need to do something custom, then you will need to kind of do that on your own, which means you're going to be diving into Linux or whatever operating system more deeply than you would on a desktop computer. The code is going to be less deterministic than on a microcontroller. Again, you're relying on an operating system to manage all of the execution for you. And on a multi-core type machine, then the operating system is going to be moving or executing the code in whatever order on whatever core it deems necessary. One of the challenges with working with a single board computer is that either you're going to be writing your code and compiling on the device itself, or you're going to be trying to cross-compile. Microcontrollers are inherently cross-compile. The tooling compiles the code on your computer and then sends it across to the microcontroller for you as part of the IDE. Whereas with a single board computer, you have to figure out how to get your code compiled. So the easiest way is generally to compile on the single board computer itself. But these are older and slower when it comes to compile times than a desktop. So you could end up spending a lot of time just compiling your code on the device. An alternative is to cross-compile on like a development laptop, but then you have to figure out how to do the cross-compile to make sure that you are compiling for the correct device type that the single board computer is running on. Finally, you may not be able to support all language options. So yes, you will have more options than C and C++, but you may not get access to the latest and greatest. And even if they do support a language, it may not be the most up-to-date version of that language that is supported. Again, you're relying on the manufacturer or the community at large to be able to create those tools that you use to program the single board computer. The final category is the desktop PC or laptop category. This is your typical desktop. You have your combination of a motherboard, RAM, hard drive, graphics card, etc. You put those together like you're building a desktop PC, and you just use that with your robot. And depending on the robot itself, you may have different form factors for the computing hardware. An ATX motherboard, micro ATX, mini ITX, etc. Obviously, the advantages of your desktop PC is that you have access to the latest and greatest hardware. So you can grab that brand new NVIDIA graphics card. You can have the largest solid state drive you need. You can have the fastest CPU processors. All of these options are available to you. And since it's basically a desktop computer, you can use any tools that run on the selected operating system. You can use Linux, you can use Windows, you can use Mac OS. You can use anything you want to program on a desktop PC or a laptop. And obviously you'd have as many options as available for libraries. Again, common ones like OpenCV or TensorFlow or OpenAI. All those things would be available because you're using a desktop PC. Anything you can do on desktop, you can do on your robot. Some of the disadvantages of the desktop PC route, though, are that you're going to be using a lot more power for your computing resource. Obviously, on a mobile robot, you want to move around and battery life is important. So you want to balance power usage with computing resources. And this is going to be a constraint on the desktop PC/laptop option. In general, it's much harder to interface with simple devices like an LED or a button on when using a desktop PC, because desktop PCs aren't generally designed for that kind of interaction. You can get a motherboard that gives you I/O probably, but they're not really designed for that. So often you will have some other piece of hardware that you're going to be using to communicate with the hardware through, like a USB I/O module for digital or analog input and output. So what are the things you need to be thinking about as you're trying to decide which of these three categories you should be looking at for your robot specifically? The first thing you should be considering is what you want your robot to do. Before you consider anything else, you have to think about how complex the behavior of the robot is going to be. If you're trying to do some kind of machine learning algorithm and you want to use AI elements, then a microcontroller is probably not going to be the choice or the best option for you. If all you want to do is read some button presses as the robot runs around and bumps into walls, then you don't need a desktop PC. You can get by with just a microcontroller. If you're somewhere in the middle and you're not quite sure, then a single board computer will be your best choice. So along with the complexity of the behavior, it's what sensors you're using. Is it a webcam? Are you using infrared? Are you using buttons? The number of sensors. So do I have 20 sensors? Do I have one? Do I have, just a single webcam? The types of sensors, again, cameras, LiDAR, or just infrared, ultrasonic. How are they interfacing with the board between the sensor and the computer itself? So the next thing you want to consider is the size and weight. And related to size and weight is going to be the available power and battery life. So if you have a very small robot, there's only so much battery you can fit on board. So you're going to have to be really conscientious of your battery life. And choosing a desktop PC running off a battery is going to impact your ability to have a small, lightweight vehicle. If you're trying to run like a drone, you probably want to use a microcontroller or a low-power single-board computer. On the flip side, if you are using a large vehicle, like a self-driving car, then a desktop PC is not that big of a deal. Now, obviously, you still want to be aware of how much power you're using, and maybe it's okay to use a single-board computer based on the complexity, but you'll be aware that the power needs are not going to be the most significant thing you need to consider if you have a large robot like a self-driving car. The next thing you want to consider is what software you're trying to run and how modular your system is going to be. If you need to run some of the more advanced libraries like OpenCV or TensorFlow, or maybe you're trying to do some ROS work, then at the bare minimum, you're going to need a single board computer, and you can't run those on a microcontroller. But if you don't care about those things and you just want to do a pretty basic thing, then a microcontroller may be fine. So here are some recommendations within each of the three categories. For microcontrollers, if you don't need anything custom, I would just recommend using Arduino or an Arduino compatible board. There's lots of tutorials online. There are lots of open source and free or easily available libraries, and they're just really, really easy to use. If you do need something custom, then go ahead and just select whatever chip you want, but you're going to have to learn a lot more. So this is really an element where you're going to be learning about microcontrollers and more low-level board design if you need something custom. But if you don't need that, and most people who are getting started don't need that, I would just start with an Arduino compatible board. If you decide you need a single board computer for your robot, then I'd probably recommend the Raspberry Pi to start, or some other Pi clone. I know that Raspberry Pis are hard to get right now. Hopefully the shortage is over soon. But the Raspberry Pi again is open source, readily available, lots of tutorials, so it's a great place to start. If you know that you need something more complicated, then the NVIDIA Jetson ecosystem is a good option. I also just learned about the AMD Xilinx Korea. That's a good place to look at as well. This is only really if you need something way more complicated and you're trying to run like some kind of machine learning elements, or you really are going to use that GPU. The price difference between the NVIDIA Jetson and the Raspberry Pi is exorbitant. And what I've seen is that a lot of people just end up using the Jetson Nano as a very high-end Raspberry Pi. They're not really doing anything more complicated. They're just trying to eke out more CPU because they're not sure if the Raspberry Pi has enough CPU cycles for them. So start with the Pi if you can get one. Hopefully they're cheap again soon, unless you really know that you need something more complicated. If you think your robot is going to need a desktop PC or a laptop, or maybe you just have some old laptop laying around and you want to use that to kind of start getting into robotics, then use whatever you have available. Right? An old laptop is great. An old computer is great. You can even use whatever operating system is on there, Linux, Windows, Mac OS, to get started. In the long term, you're going to need Linux, probably. There's just so much more resources available within Linux. Most of the robotics community is using Linux. One reason is because a lot of single board computers use Linux. Another reason is because it's free and open source. So a lot of academics research is using Linux. They don't have to pay for licenses. And there's a wide availability of hardware now that will run Linux. So regardless, if this is the route you want to go, you're going to have to kind of get more comfortable with Linux. But to get started, just use your whatever laptop or desktop PC and start playing around with stuff. You probably will have to get some kind of I/O device module to interface with like LEDs, etc. But it could be a very easy way to get started. Now you might realize I just basically recommended use the popular thing. And yes, that's pretty much what I'm saying. These things are popular. They're the most common options: Arduino, Raspberry Pi, NVIDIA Jetson. And they're popular for a reason. They make things much easier to get started with. And there are lots of tutorials and lots of resources. So if you're trying to get started, you don't really know what you're doing, just go use the popular thing. If you're interested in diving deeper, you don't have to start with the most popular thing or use them, but just know that you're going to have to learn a lot more before you can really break through and make progress. One of the reasons robotics is so challenging is because there's a lot of work kind of on the starting on-ramp that can be an obstacle. So these tools like the Raspberry Pi and the Arduino has made that on-ramp easier, and that's why they're so popular, even by people who know what they're doing. So don't reinvent the wheel. Start, have success, and then you can go back and learn more if that's something that interests you. Selecting the right computing resource for your robot can be difficult, and there's a lot of things to consider. You may even need to use some combination of the three options. So maybe use a microcontroller for your motor control, a single board computer for your camera algorithms, and then a desktop PC to run your machine learning processes. Those are also options. But just keep in mind the considerations that I laid out earlier, and make sure that you're not just throwing everything at your robot. I hope this video helped at least point you in the right direction when you're trying to figure out what computing resources you need for your robot, or maybe what robot kits you should be considering as part of your robotics journey. That's it for now. Talk to you soon. Later.